Hello all. So in this video, we will learn something about logistic regression. So logistic regression is a machine learning supervised learning algorithm which helps you to classify your classify your target variables. So basically, if you speak, this is a logistic regression curve, and this is a linear regression curve. So first of all, we have to understand that logistic regression is a supervised machine learning algorithm. Means it will have features like f1, f2, f3, and it will have a target variable y. Target variable can be classified into binary classes or the multiple classes. For simplicity, we will take the binary class. Binary class means yes, no, 1, 0, 1, -1, something like this. So it's a supervised machine learning algorithm. But why then you think regression has been given here? Because here my yi or my target variable is categorical. It's categorical. So for that, we can understand from the example of linear regression. So linear regression is actually a algorithm which fits a line, and it is used for continuous variable, but this can also be used for classifying the points. You can see how. So suppose I say that this x is weight here, and if someone is having more weight, you classify it at 0, which is called obese. Suppose classified 0 is non-obese. Non-obese. If my weights are less, it is called non-obese, and if my weights are more, you call them obese. A simple example. So here, and there will always be a cutoff, because since it's a continuous line, so it will have 0.5 as a probability. So if 50% if suppose I'm taking this person here who has high weight, and if I drag this line up to here, so my probability is more than 50%. So it is classified what? It's obese. Simple. It's very simple. So suppose this is my line. One second. So this is my line here, and if my weight, and this is my 50% thing, and if my person is having higher weight, you can drag this and you can get it. The probability is more than 50%. You will get some. You can classify as y is equal to 1. And if my weights are, if the person is weighing less, and you can always drag this line, and you can see the probability is lesser than 5 or 50%, and you can classify them y is equal to 0. So actually my linear regression is doing the good job. My linear regression is doing the good job of classifying the points also. So why do I need the logistic regression? So for this, you could understand that first of all, my linear regression, my probabilities are not in the range of 1 and 0. Because suppose I have a point here, and if you drag this, it will come to something like 5 or 6. So though we can claim that something which is above 1 also, we can take it as y is equal to 1. But practically it does not make any sense that first of all, you are just taking the probabilities values between 0 and 1, and if your point is extrapolated above 1, you will just classify it as 1. So second number point. So always in a logistic regression, what your point has, how your best fit line is actually fitted. So if you have all the points up here, something like this, all these points. So as per your point, a best line is fitted considering the length of the distance of your actual point should be as minimum as possible. So these distances should be as minimum as possible here. So this is how a best fit line is created. So suppose if you have an outlier here, for example, you have an outlier here. So my best fit line won't be like this. It will change like this so as to compensate or accommodate this outlier. So my linear regression model are very, very sensitive to the outliers, because then my best fit line will change. And number two, even during the classification, my extrapolated values come more than the range of probability. So my range of probability is 0 to 1, but my point comes beyond that, though we can classify it primarily just because of intuition between 0 and 1, but that does not solve our purpose. So with this, we have a logistic regression in place. What a logistic regression does, it actually, why the first of all regression term is used? Because it gives a continuous probability, just like a linear regression. This is the cutoff. So we can use this. So this is the prediction. So this is my best fit line in linear regression. What happens? It's the same like linear regression. What it does, first we use the best fit line to classify two classes as per linear regression. Then we kind of squash it or we compress it. So we use sigmoid functions to do that. A sigmoid function is 1 plus 1 by 1 plus e power minus x, y is equal to. So this is a sigmoid function. So when you understand what is a sigmoid function, what it does, it actually tapers off like this. So even though your points are in outlier, what it will do? It will just taper off, and the point will be something accommodated in this. So logistic regression by far is much more robust to outliers than the linear regression. So this is a process which shows this. So a normal regression best fit line, then a line is used for classification, and then it is transformed using a sigmoid functions so that it is robust to outliers. So this is how a logistic regression works. And why is it regression? Because it is just a transformation of linear regression. It's just a transformation of linear regression. Why? You always find the best fit line here, and then you classify with the help of best fit line, and then you squash it. That is why a linear regression, this is a transformation of linear regression. And why? What is the disadvantages of linear regression? That when you use it to classify, it is the extrapolated points are not in the range of probability, and second thing, it is sensitive to outliers. So please get this point clear. There are two major reasons why linear regression is not used for classification. One is this reason, the probability range, and second thing is it is sensitive to outliers, which my logistic regression is not. So first of all, you should know why the logistic regression is used. So this is why the logistic regression is used. Now we will see the intuitions or the basic interpretation of logistic regression. So for that, we have to start with the equation of line, because what happens is the first point But the first step is to find the best fit line only. Best fit line. The first step is to find the best fit line. So if my two classes, suppose my two classes, say positive class and negative class, it should be linearly separated by this line. So you have to know what the equation of a line is. So this is a vector equation of a line. It is very simple. If suppose you draw a normal vector to a line, this is n vector. So you can say, and this is suppose this is point P here. This is point P on your line. And this is a vector perpendicular to this, which is x. So what you can do, first of all, you can say that P dot n will be equal to 0. Why? Because a dot product is always P dot n dot cos theta. So theta will be 90 degree. So it will be 0. So this is the major equation. And since it is parallel to this, the general equation you can write it like this: n dot x minus p is equal to 0. All these are vector. This is a vector form of a line. But general form of a line, you know what is a general form of a line, and it is y is equal to mx plus c. How you can derive this point? So suppose this point is here. This line is passing through here. This is c. This is y-intercept. The equation. The point is 0, c here. And suppose if you have a point x by y here, so this theta is what is called m, and which is tan theta. So this is tan theta. What is tan theta? Perpendicular upon base. So perpendicular is this line. It's this line. So what it will be? Total y minus c. So it is y minus c and x minus 0. And if you substitute it, it will be y is equal to mx plus c. A general form of a line is this: ax plus by plus c. And you can ax plus by plus c. And you can change this to y is equal to mx plus c. You put ax and c here, and then you can see. So basically this is what the equation of a line is. So in 2D, when you have two set of classes here, positive class and negative class, so a line will separate it. But in 3D, you will have to get it separated by a hyperplane. So this is a simple snippet where I have told you how to get the equation of a line. So suppose this vector, equation of a plane. So this is a plane, because in 2D, a line will be there. In 3D, it will be a plane, and in 4D and above, it will be a hyperplane. So in 4D and above, it will always be a hyperplane. So here, this is a normal vector n. This is a point P which has a r vector, and these 2 points are there. So you know cross product, if AB cross AC will actually give you a vector perpendicular to this, which is n. So this is how you can actually, this is the derivation, you can actually see it. So if AP is perpendicular to n, so dot product, which is AP dot n, will be equal to 0. This is r minus a. Why? Because r is this and a is this. So r minus a will be this effective vector. R minus a dot n will be 0, and then the points are substituted. But in general, just like a line has an equation of ax plus by plus c is equal to 0, a plane has a general equation of ax plus by plus cz equal to 0. Why? Because it is a 3D figure. It's a 3D dimension thing. In vector, we have this equation of a line. What is this? AB cross AC is a normal vector, simple, a normal vector. And what is this? R minus A? R minus A is a general point on a plane. So basically, you can convert this general equation of a line to a vector form, something like this. W transpose X plus B is equal to 0. Actually, the equation of plane which we use in machine learning is pi is the plane, which is Wx plus B. How is this derived? This is from simple this derivation. This WT is the normal vector. Why transpose? Because generally when we write vector, so we actually mean a column vector. Column vector means this type of vector. But why we have transposed it, we have made it to a row vector, and then our X will be a column vector here. So our X will be a column vector here. So suppose this is a row vector. So I have for example, 1 row and 3 column, and this is 3 rows and 1 column. So what my effective dimension of Wx will be 1 cross 1. So this is how a pi the plane equation is used for your purpose. So now, since we know a pi is W transpose X plus B is the equation, wherein this is the plane, this is the W, and which is 90 degree to this. This is a equation of plane, and this will help you to separate your two classes. So in the next video, we will see what is the actual geometric interpretation. In this video, you understood number 1, the linear regression cons, why it can't be used for the classification. Second, the pros of logistic regression, and third, basics of lines and planes. Geometric interpretation of logistic regression. So in the last video, we look at the basics of logistic regression. Here we will understand the geometric interpretation. So there are basically many types of interpretation here. So mainly 3 types of interpretation people generally look for. One is geometric, one is probabilistic, and the last one is loss minimization. We'll try to discuss all the 3 through this video. So this video is basically for the geometric intuition. So here there are 2 figures which I have shown. This is a line in 2D which is separating my positive and negative class, and the similar in a 3D how it would look. This is a plane which is separating 2 types of point, which one is positive and second is negative class. So when I say a positive and a negative class, so it does not mean that positive is something which is important and negative is not important. It's just the label. It is always a label, remember. It's a label, and we are classifying the labels. The labels can be anything. Suppose you have some features. Suppose you have there is a machine learning algorithm which predicts whether the person is a boy or a girl. Okay? So you can always label a boy or a girl +1 or -1 either way, and then you will have the features like hair length, nail length, and all those things. So these all features will be there, but you will always have the label of the target variable. Label, this is positive and negative label. This is W. Always remember, the points on the same side of W are positive. Points means the distances, the DI. What is the distances actually? So from the last video, one thing we missed, that when we want to find the distance, what we use, we simply use W. This is the equation of my plane. This was the equation of my plane. 1 second. Yeah. So WT into Suppose this is the point from which we want. Suppose this is xi point, this is di point, and I want to find the distance di. So what I will do, wt into xi into mod of wt. It's a basic, we can say, geometry. So this is how you can find the distance. I want, for the simplicity, to keep this wt as a unit vector. So if I say the modulus of wt will be 1. So my distance will be this. This is a distance. So from distance of my these point, but what I'm telling through this, that any point which is on the same side of direction of w. So my w is in this direction. So all axes in this directions will be positive. And all xj in this direction, the lower direction, will be negative. So which side is negative or opposite to the w. So what I can say, suppose my di is positive, which implies wt into xi is greater than 0. So this makes my one class, and if my di is less than 0, it makes my second class. Now which class is this? We will see in a while. So here, if suppose, let us see, this is a positive point and this is the this is a positive label and this is the negative label. This is the distance. So when you have a positive level, you have a target variable yi is equal to +1, and when you have a negative label, you have yi is equal to -1. Okay, now if this plane or this point is my classifier, this is my classifier which classifies these 2 points. This plane is acting like a classifier. It classifies both of my points. Now what I will do, if my classifier is doing 100% of a job, it is classifying both the classes into positive and negative. So what can be done? Suppose this is greater than 0. If I will multiply this target variable in here, so if I multiply yi into wt into xi, so my yi will be positive only, and this wt into xi is greater than 0. So product is greater than 0. Similarly, all my x's are negative. Why? Because it is on the negative side or the opposite side of the normal vector, sorry. In this case, if I multiply by yi into wt into xi, yi will be negative and this will be negative, this product. So overall, this will again become positive. So this makes me, this gives me a wonderful conclusion that if my classifier is properly separating both the classes, then the product of yiwt into xi will be always greater than 0. Okay, now let us see case number 2, second case basically. So if suppose this is my plane, this is my positive class or class label, this is my negative class label. If suppose my classifier is not doing the 100% of the job and it is misclassifying one of the point here and misclassifying one of the point here. So in this case, what will be the distance? The distance will be greater than 0 only, because wt into xi will be greater than 0. But when you multiply this, now this I will be -1 and this I will be +1. So if you are multiplying yi here. So yi into wt into xi will become 0, less than 0. Why? Because this is negative. Similarly, here I always have di less than 0. Why? Because x's are up on the opposite side of my normal vector. But when you multiply yi here, so if I multiply yi here, it will be less than 0 only. So I have a wonderful case that if my classifier is separating my point correctly, then I will have yi wt into xi greater than 0. Perfect job. Perfect classification, I can say. And if my yi into wt into xi will be less than 0, then my classifier is misclassifying the point. So, to measure the performance of my classifier, I want this condition. So, I want to maximize this. Now, suppose my data set is like this. I have m rows and n columns. Sorry, m columns and n rows. Oh, I get confused between rows and columns sometimes. So this is m rows. Sorry. Let us remove this. So this is my data set which has m columns and n rows. Suppose this is ith rows and jth column. So I am taking this x as xij. What will be xij? It will be a vector with x11, x12, x13, something like this. So I will take all this and represent it as xi. Why? Because I will have rows and columns. So I am clubbing all this row vector x11, x12, x13 as xi. I'm just representing it with I, not taking with rows. So this is how I'm representing. So now what will happen? I want to maximize. So if my data set is this, m column, n rows, what I will do, this is n rows, I have n rows. This is my yi. So my yi can take the value from 1 to n. Similarly, if I have my x's, so my x's, if I take this one row, this full will be I. So it will also be ranging from 1 to n. To what my optimization function will be? It will be to find the best W which maximizes summation of n wi into wt into xi. Because what happens is my plane is categorized by only two things. One is the normal vector and the second is the intercept. For this, I am not taking this intercept because I am considering my plane is passing through origin. Passes through origin. So I'm not taking this b here. So if I find my W or the normal vector, my job is done. So since xi and yi always comes from the data set, so xi, yi are fixed. It cannot be changed. According to this, I have to find this W and I have to maximize this. So if I have n data points, so I want most of it should be plus one, so that I can maximize this. This is the optimization function. But what is its shortfall? Let us see. So let us see what can be its shortfall here. This optimization function. So suppose I need to find my best W which maximizes my summation of 1 to n WTYI into XI. I want to maximize this. Now what is the problem if suppose there is a cooked up example? If these are my positive classes and these are my negative classes here, and suppose these are equidistant to the plane, these both point are equidistant to the plane and the distance is 1. This is my W. Okay, so this part W t into x, which we said earlier, was distance. But when I multiply with y, so y can only take the value of plus 1 and minus 1. So it will not change the magnitude. It will just change the direction. So we will say this a signed distance. Signed distance. So if this is it, so I can multiply. If this is 1 unit. So what will this say? So this is plus 1 yi. So here yi into wt into xi. So yi will be plus 1 here. Wt into xi will be plus 1 here. So all this point will have 1 unit distance plus 1. So what I will say? Plus 1 into 5 will be 5 units. Similarly, here my yi will be minus 1, but my xi will be also minus 1. So all this will be positive again. So this will also be plus 1. So overall, my distance, my signed distance or summation of y into wt into x comes out to be 10 units. 10 units here. But for example, these were my points. Suppose I have one misclassified point here whose distance is 10 units from the plane. This is a misclassified point. Currently, my summation is coming to be 5 plus 5, 10 units. And this has the this has the minus 10. Why? Because yi will be minus and this will be plus. So wt into xi will be plus. So this will come to be minus 10. Or suppose minus 100 I say. This is a 100 unit. So what will happen? Now my summation will be plus 10 minus 100, which is equal to minus 90. So I could not maximize my optimization function. What I did, I minimized it. Why? Because I had one outlier point. So what my model will do, it will shift. It will be like this now. Now what my model will do, my model will, this plane will be flipped up. It will be like this. So this is my 1 point and these are my classified points. Why? Because of this. So this is actually a very a bad classifier, I would say. It's a very bad classifier. Why? Because it is classifying one point correctly maybe, and rest other pointers all not proper. So this classifier is very bad because it is just classifying one correct point, and all these positive and negative classes it is classifying as single class, which is a positive class, which is not okay. So I can see that presence of outlier actually makes my job difficult. So I would say that presence of my classifier, presence of outliers makes my classifier bad. So what to do this? Now my sigmoid functions come to picture. So if my classes are separated by this plane, and if suppose there is an outlier here, my sigmoid functions will be asymptotic. What it will do? It will try to quash this. So my best fit line will be this only. My best fit line will be this only, or best fit plane will be this only. But it will taper off in the outlier section. So suppose this is my positive class, this is my negative class, this is my point. So what it will do? This will be a tail of a sigmoid functions which will make it squash, or which will restrict my range or boundation between 0 and 1. The sigmoid functions look like this: 1 plus e power minus x. It actually makes my model robust for outlier. So that is why we use sigmoid function. Here, this is my best fit line always. And these both tails take or compensate the outliers basically. So if these two points are like this, so this is one class, this is another class, this is the best fit line, something like this. For example, this is my best fit line, this is my first class, this is my second class, and then outliers will be accommodated in these states. So that is how sigmoid functions helps us. So in the next video, we will extend our discussion of this logistic regression. This is a geometric interpretation which we have seen, but we will also see a better version of this geometric interpretation and see how we can use that as our loss function. So basically, it is very much sensitive to outliers. So guys, listen, you have to understand how a logistic regression and a linear regression is correlated. So if this is my graph, so what it does, my logistic regression also finds the best fit line first, and then it tapers. So this tapering effect, what it does, tapering effects actually helps me to compensate for my outlier. That is why in this equation, we will not be having any kind of tapering effect which will compensate for the outlier. For this, my graph will look something like this only. It's just like a linear regression plane, which the line extends to positive infinity and negative infinity. And then again, in the first video, what we have discussed, it will pose two things. First, it will be sensitive to outlier, and second thing, the probability value will not be contained between 0 and 1. So sigmoid functions comes to rescue. So what is my sigmoid function? So this part of my sigmoid function, this particular part is the part of my best fit line. Best fit line. And what is this tapering thing does? It actually is used to compensate the outlier. So for example, suppose I have some x point here and now I want to predict its class. So to predict its class, I will extend, I will drag this projection. I'll basically project it to my y-axis here, and then it will cut here. So it will give me one class, which is a positive +1 class. And this will give me a 0 class. So this is how a sigmoid function will help me to compensate for my outliers. One thing you would also understand that sigmoid functions basically works between 0 and 1. And this derivation of the optimization functions, I have done it with +1 and -1. I will explain you why I have derived it with plus and -1, +1 and -1, and why this is 1 and 0. Basically, these are two types of different interpretation. One is geometric and one is probabilistic, but both are one of the same thing. So the point to be noted here is my general optimization function is very much sensitive to the outliers, and thus my sigmoid functions helps it to compensate for the outliers. Now, what I will do, I will take the help of this sigmoid function and transform my transform my optimization function. So my optimization function has basically these three types of values. So if I'll transform it, what it will become? It will become something like this. Why? Because what is this? This is x. So y function of x is 1 plus e power minus x. So if I will transform this, what I will do, function of x will be wt yi into wt into xi. And what is this function? This function is nothing but a sigmoid function. So when I will use it to transform my optimization function, so it will take the shape of this. Now our optimization problem has changed to this. So now I will again find my best w. Always remember, whenever I am finding my best w, I am finding a plane. And if I am finding a plane pi, which is separating my positive and a negative class, my job is done. So I have to find this best w now, so that such that it maximizes my this part. I have to maximize this part here. So let us see how. See, on a general case, we can also assume that what minimum or what maximum value it can take. Okay, but we will now understand it much more deeply as to how practically we can help this optimization function to attain the result, to attain the optimization. So this is what a monotonic function property will always help me here. So what is a monotonic function? So any function which is either always increasing or always decreasing will be a monotonic function. So monotonic function, this is a monotonic increasing function, wherein whatever you change in the x value, whatever addition, as my x values changes, my y value will always increase. Here, if my x values changes, my y value will always decrease. This is the monotonic function. Even if you will decrease, so as and when my x will start increasing here, this function will increase. And here, if my x is increasing, my function will decrease. So this is, and this function, such kind of functions which have the basic periodical changes that it will increase or decrease. That's not a monotonic function. So there is a very beautiful property of a monotonic function. So I have chosen a log function. So log function is a very amazing function in my mathematics, which helps you to give you a lot of meaningful insights. For example, you also know that I can change my multiplication to addition by use of log. So log is a very amazing function and is often used for the optimization result. So my log function, my graph of log function is like this. It is ever increasing. It cuts my x-axis at 1 and it gets increasing. So whatever value, whenever I will increase my x value, my log function will always increasing and it will go till infinity. And here it will go to tends to 0. It will touch my y-axis here. Okay. So this is my monotonic function. So what I want to interpret or I want to use is, if suppose I have a function, say x square. I have any function that is not mandatory that if it is a monotonic or not. Suppose I have any function which is, for example, x square, and its minimum value is 0. For example, I'm just considering the minimum value so that you can understand. And my g of x is log of x, which is a monotonic function. This is a monotonic function. My claim is, if I combine these two, if I will combine my g of x with the f of x, I will get the same result. I will get the same minimum value or the maximum value whatsoever it is. So here our claim is, suppose I want to minimize this x star such that I want to maximize f of x such that I find the best x which minimize f of x, and f of x is x square. So I know from the graph that my minimum value of this function is 0. So I have written it 0. Similarly, if I use g of x and f of x together, and I find g of f of x, minimum value of that, it will also be 0. Its x star and x dash are both equal. And if you will plot the graph of log x square, it will be just like this. Basically, it will be a mirror image of log of x. So my claim is, if I have any function, you can try it by yourself also, any function f of x, and if I combine this with a monotonic function g of x, the property of what I have with g of x will be applicable to my g of f of x. So g of f of x will have the same property. And even if you can see it in a very logical manner also. So if my f of x is something, I can replace x by g of x here. So what will happen? This will become f of g of x or vice versa, whatever. So all the property of my f of x will also be applicable to f of g of x. And similarly, all the property of my g of x will be applicable to f of x if I'll replace my x in g of x by a function. So here what I'm trying to do, I'm trying to make a standard formation of my optimization function by using log. And you already know log has a very much important function which helps to reduce the granularity of my optimization function. So now this function, this is my optimization function. What I will do, I will use this function as f of x, and I'll use this function g of x as a log x. Okay. So what I will do, I will plug this f of x into this g of x here, which will give me g of f of x, which will be like this, which will have the same property as my log x. So my optimization function will become w star argmax of this into log of this. And as you know, log of 1 by something will be equal to minus log of something. So using this property, I have simplified my equation to this. So now taking this negative sign outside, now I have to maximize this. But a negative sign will obviously mean that whatever you do to maximize this anyway, it will be negative only, it will minimize only. So with I will remove this minus sign and I will change this argmax to argmin here. And for simplicity, I have taken zi as yi into wt into xi. But this is my basic optimization function. W star is equal to argmin of w, and we have to find the best w such that it minimizes log of 1 plus minus yi into wt into xy. This is my final optimization function. But there is some problem with this also. Let us see what is the problem. So this is my final optimization function. I have replaced this zi is equal to yi into wt into xi. I have replaced it with zi. So I have plotted a graph of y is equal to 1 plus e power minus x log of this. I have plotted the graph of this. So my graph is something like this. You can always check from Google also what is the graph. So my graph is such that as my x tends to positive infinity, my y tends to 0. This is how this graph is working. This graph of this part. This is the graph which I have plotted. Y is equal to log of 1 plus e power minus x. I have this graph. So this graph works in such a way that as and when my x increases and goes till positive infinity, my y value tends to 0, because see, it is getting flatter and flatter when it starts touching the x-axis, and finally it touches the x-axis completely. So now my value will be 0, y value will be 0. So my task was to minimize, find the best w such that it will minimize this optimization function. So now I can know that since the minimum value this function can go is 0. So log of 1 will be 0. So you know that log of 1 will be 0. And log of 1 plus some small value will be tending to 0, approximately 0, but anyway not 0. So one thing I am very much sure that my optimization function which I want to minimize can take the minimum value as 0 and maximum value as infinity, and it is not defined. Maximum value, it is not defined, but minimum value, I can take it 0. Now, what happens if my optimization function is minimized to the 0 value? So, if my zi tends to infinity, then my optimization function will tend to 0. This means z will tends to infinity and my wt will tends to infinity, and my optimization function will reduce to 0. It will get its minimum value possible. So my optimization function can take the minimum value possible and hence does the best work. So if my optimization function is minimized to its last value, last minimum value, that means my model or my classifier or my classifier does the fantastic job. It actually classifies 100% of my points properly. So I will have 100% accuracy on the trained data. 100% accuracy. And what it means, 100% accuracy on the trained data or the data set which we will use to train it. But remember, if I am getting 100% result in my training data, that does not mean that I will get the same result in my test data. Let us see how. So this actually making my optimization function as 0 overfits my model. That means my model does not learn anything general. It is just mapping each and every points possible and will only work with these particular points. If only points with such coordinates will be given, then only it will classify it properly. Because it is not learning the general trend of my data set. It is learning a very, very individualistic individualistic kind of information, and thus it will make him overfit. What we want, I don't want 100% accuracy, but I want my classifier or my model to understand the general trend of my data set, so that if my trained data is classifying suppose 90% of my point properly, so it should also provide nearly 90%, it should have 90% performance on the test data as well. So I want this, I want a normal separation. I don't want a accurate or 100% separation, or it will make my classifier overfit, and overfitting means my classifier will have high variance and low bias. We will see about what this means, but for time being, you just understand a overfit model has a high variance and a low bias. So now we need something, some tools to reduce this overfitting thing. So for this, we need regularization. So there is a huge and a very deep topic in my machine learning algorithm, which is called regularization, and which is used for various machine learning algorithm. It is not only dependent on logistic regression. It is used for many machine learning algorithm. We will not go in depth into this because it is a very vast subject and beyond the scope of our discussion. But we will understand what this regularization term will do. What I will do, I will add along with my optimization function, I will add a regularizer, which is lambda into our weight into square, which is a L2 regularization. I can also use lambda into mod of W, which is my L1 regularization. And I can also use both of them together in my elastic net regularization. So I have three types of regularization. On the face value, you can just understand. Now, what my regularization term will do, whenever this function will tend to infinity, so as to optimize my W, so that it will attain a zero value, this will help to reduce. It will not allow this function to tend to negativity. Infinity. It will not allow this function to go to infinity. So there is some sort of a tug of war. I'm just giving you an intuition of regularization. There will be a kind of tug of war between these two terms here. this term and this term, this term and this term, they will oppose each other. This function will try to go to infinity, and this function will stop this function to go to infinity. And that is why this will be a huge tussle between both of them, and they will meet in some very sweet spot. Very sweet spot they will meet, and that will be my actual optimizing function, where my minimum value may not be zero. My minimum value may not be zero. It will be some integer value or some continuous value, but that will give my just right separation. Just right separation. So this is how a whole logistic regression work. In this video, I have explained you how a logistic regression is interpreted from the geometric perspective, geometric intuition. Why? Because it is very much easier to look at the functions, to look at how it is done, why it is done, and it is very easier to recognize. So this is how my geometric interpretation of a logistic regression works. We can have a probabilistic model as well. I will just give you an intuition. Many textbooks will give you a probabilistic model, but let us see it in a very brief part. So this is a PDF from a textbook. I have just taken it out. I will just give you an intuition as to how a probabilistic model will work. So for a probabilistic model, there are two major assumptions which we take. Two major assumptions. Number one is all x's are independent of each other, or all the independent variables are independent of each other. Means they are not correlated. This is my assumption number one, which is not practical in real life, because some or the other way your independent variables will be correlated, but for the proof point of view, or for getting the ideal optimizer, we will say that my axis or my independent variables are independent of each other. Second major thing, you can see here, I am taking a Bernoulli distribution 1 and 0. There are only two discrete outcomes, 1 or 0. Bernoulli, I am assuming Bernoulli distribution or binary distribution in short word. Well, my logistic regression can be used to classify multiple classes, but for the proof we are taking the x's are independent of each other, and we have a Bernoulli's distribution here. So I will have a loss function. So my interpretation start with a loss function. What is a loss function? So a loss function will be such a function which will give you, this is the y hat will be a probability, and y will be the class. So this is a continuous, this is a class. So this can be either 1 or 0. Always remember, in a probabilistic interpretation, we always use my 0 and 1 here like this. So now what I will do, I will find my conditional probability to get a class y given x's. So what I will do, I will put this like P of yi, P of yi into 1 minus P into 1 minus y. Why? Because I am considering, suppose I have one class as one probability, or one class is labeled as 0 and other class is labeled as 1. I am mixing both, or I am combining both of them. So suppose if my probability I will find, and I will say that suppose my yi is 1. So yi is 1. So this term will get in term will reduce to 1, and this will turn into a probability. And suppose if I'll say, so I'll write it here, if I will say my yi is 1, so this will reduce to py. If I'll say my yi is equal to 0, so what will happen? This will reduce to, this will be converted into 1 by p of 0 will be 1. And what it will do? So it will be like 1 minus pi. So I have combined the probability of my positive and a negative class into a single equation, and then I have differentiated it, and differentiation will give me my loss function. So in the next video, in the next slide, you can see that this is my loss function as per my geometric interpretation, and this is my loss function as per my probabilistic interpretation. So both of them are the one or the same thing. It's just the way I have written it. It's just the way that we have proved it. Only one difference is there. Here my yi is either -1 or +1. Here my yi is 0 or 1. Only this difference will be there. And you can check it. You can always check it. You can put your yi as -1 here and yi as +1 here. You will find yi is 0. And you can check both of them will have the same final formula or the equation. So this is how my probabilistic function will work. So basically, in short, for logistic regression, we have seen probabilistic interpretation and geometric interpretation. You can go to much more depth about what is a probabilistic interpretation is, but I have given you the basic idea. But the geometric interpretation is my favorite and very easy to understand. So I hope the concepts of logistic regression would have been cleared from this video. If you like our content, please like the video, subscribe the channel and share it with others.